Hello, in this introductory lecture to linear systems, we want to talk about special functions and do a little bit of a math review. Now, some of this may be very familiar to you. Others of you, it may be that there are some topics here that somehow in your exposure so far to mathematics, these got omitted. A lot of times, engineering students don't take trig anymore. Sometimes in pre-calculus, complex number math is not really thoroughly covered. So I think it's certainly worth it because this class is essentially a math class. It's an applied math class, but we do use a lot of mathematics, some of which you may have seen, some of which you may have not seen in a long time. So I think it is worth it to go through some of the introductory materials. In your textbook, this is found in the appendices, which interestingly enough in your textbook are at the beginning of the book. So there is an introductory chapter / section that contains these materials, and so we'll go through them by way of review. Probably we'll split this material into 2 lectures so that it doesn't get too lengthy. You can spend as much or as little time on the math review as is appropriate for you, but I do find that even in Circuits 2, when students have already had linear systems, some of these concepts continue to be a problem, so I think it is worth going through what's in the book. So the first thing that we want to do is define what is an imaginary number. You should have seen this in circuits. Basically, the definition is done with imaginary number squared is equal to -1, which then leads to the square root of -1 is equal to plus or minus j. In electrical engineering, you've probably already been told that in electrical engineering, the square root of -1 is referred to as j, not I. Throughout mathematics and physics and other technical courses, you will see imaginary numbers with the lowercase I. In electrical engineering, it evolved as J simply because we refer to current with lowercase I. So to avoid confusion, J was used historically, and that's what we continue to use. So a lot of people ask me, oh, are you going to grade it wrong if we use I instead of J? In this semester, a lot of things are graded automatically looking for characters, but certainly if it's obvious what you're meaning by I instead of J, then that's not an issue. However, I really strongly encourage you throughout electrical engineering, you will always see J. You will not see I. So if you're not in the habit of doing that, please get in the habit now. All right, so complex number representation, and many of these slides are taken directly from the textbook. So if you are a person who is more comfortable reading the information in the textbook than listening to a video lecture, then I more than encourage you to do that. As I said, this particular lecture, we're just taking information straight from the textbook. But I will go through and point out what is and is not important. So a complex number in engineering and physics and everything that I've ever done, I've never used the notation parentheses a comma b. I've always used the notation a plus jb. It's often referred to with some kind of title. In this case, you can see in equation b.1, they use z, so z is equal to a plus jb. The notation real of z is equal to a is a common notation. Basically, the real part of the complex number is the part that does not contain a j. The imaginary part is the part that does contain a j. So in rectangular or Cartesian form of the complex number z, a is the real part, b is the imaginary part, and it's written a plus jb. A lot of times the notation for complex number is usually given in bold, so this book is a little bit unusual. If not bold, sometimes a little squiggle or a straight line is written over the complex number representation, so it's a little bit unusual in this book that they don't do that, because typically that is what you see. Usually real and imaginary are written as script in most mathematics and engineering textbooks. So if you see me write this in cursive, that's all it means. If you see me put a squiggly over my z, it just means it's complex. So we can plot a complex number. It does not plot. It plots kind of like a vector. So it'll have in the complex plane, The vertical axis is always the imaginary axis. The horizontal axis is the real axis. So you plot it just like you would plot a vector. You plot the real component A and you plot the imaginary component B. And so you go to the point AB on the complex plane. And then the actual complex number itself is represented by the line. Oftentimes in text you will see it drawn with an arrow at the end. In fact, most textbooks draw it with an arrow at the end. This textbook, once again, does not, has a little bit of different notation. You'll notice that the length from the origin of the complex plane to the coordinates for the complex number z has a length of r, and so that's referred to as the magnitude, sometimes also referred to as the amplitude of the complex number. We tend to call it amplitude because typically in electrical engineering we're talking about currents and voltages, and so amplitude would make sense, but it can also be referred to as the magnitude. You'll also notice that there is an angle associated with displacement in the counterclockwise direction from the real axis. So we can also write this in what is known as polar form, but you'll notice if you look at the rectangular coordinates and you relate those to r and theta, that A is equal to r cosine of phi, and B is equal to of theta, and B is equal to r sine theta. So as a consequence, if we write z is A plus jb, and we plug in into sine and cosine, substituting with r cosine theta and r sine theta, then we find that we have the following form in terms of r and theta. Applying Euler's formula, e to the j theta is cosine theta plus j sine theta. So if we apply Euler's formula, we will end up with, let me get out of pen and into arrow. So we have A is r cosine theta, B is r sine theta, and oftentimes in polar form the complex number is written as shown in this equation here, where z, the complex number, is equal to z with the absolute value sign, which is the magnitude of z, and equal to r, and then e to the j times whatever the phase or angle associated with z is. So as we've seen from the figure, the angle z is theta, the magnitude of z is r, so we could write this as z equals r e to the j theta. The angle theta can be found from B and A by taking the inverse tangent, and I'll refer you back to the complex plane figure to look at that, and then the magnitude can be found using the Pythagorean theorem. The reciprocal of a complex number is the reciprocal of the magnitude, and then e to the minus j theta, where theta was the phase or the angle that the complex number forms with the real axis. The complex conjugate of a complex number, or conjugate of a complex number, if z is equal to a plus jb, the conjugate is a minus jb. If z is equal to r e to the j theta, the conjugate is r e to the minus j theta. So it's reversing the angle on the phase if it's in polar form, or it is reversing the complex, or the imaginary part of the complex number if it's in rectangular form. There are some useful identities. E to the j pi is equal to minus 1. Easiest to visualize that if you look back at the figure. E to the j pi, pi would be 180 degrees, so that would plot on the negative real axis. So it's equal to negative 1 because the magnitude multiplying the exponential is 1. And then, of course, if you add any integer multiple of 2 pi, you end up right back where you were. If it is e to the j times 2 pi n, then that's equal to 1. Because if n is an integer, then that would basically just be 2 pi, so you've gone around one full circle. So e to the j times 2 pi is 1, e to the j times 4 pi is 1, and so on. If you have pi over 2, that's an angle of 90 degrees. So if it is 2 pi n plus pi over 2, then you are on the vertical axis in the positive direction. And so that's basically equal to j, an imaginary only component. And if the pi over 2 is negative, then that's going to point in the down direction on the plot, and this will be equal to minus j. I'll use these a lot throughout the semester to simplify things, and so you should be prepared to recognize those throughout the lecture. So there are some examples in how to convert from Cartesian to polar form, and I won't belabor these an incredible amount because literally it is just plug into the formula. We can find the magnitude of z. So given these expressions, 2 plus jz, and there are several parts to this problem, we can find the magnitude by taking the square root of the sum of squares. So in the first one, it's the square root of 13. The angle is the inverse tangent of b over a, so it's 3/2 or 56.3 degrees. And so you can then write that 2 plus j3 is equal to the square root of 13, e to the j, 56.3. Very important to, if you're not comfortable with this calculation, very important for you to learn and understand exactly how that happens. The way it happens is by utilizing and applying the correct formulas, and there's really no other shortcut. Your calculator has the ability to do this. The one thing that you do need to be careful of is, you notice in the second problem here, it is the real number that is negative and the imaginary is positive. So in calculating the inverse tangent, the real part has a negative, and so it's going to end up in the second quadrant. But notice there is some ambiguity. If you do this in your calculator doesn't know whether the negative sign is associated with the 1 or the 2. So when you get an answer off your calculator, you need to check very carefully to see if that's off by 180 degrees. This is a common and easy mistake to make. If your calculator does a direct conversion from rectangular to polar, where you enter the real part and then enter the imaginary part, this should not be a problem. Okay, and this is just more of the same. You have a copy of these PowerPoint slides, so you will be able to go back, and if you need more examples, then you have those here. Now, this is a plot in the complex plane of the complex number, and you do need to be able to look at a plot and give the complex number that the plot represents, as well as plot a complex number in the complex plane. So that's something that you need to be familiar with, and you also need to be aware of what happens with the associated quadrants. So if this is something that you haven't seen in a while, or that you haven't ever seen or ever practiced, now would be a really good time to do some of the practice problems associated with working with complex numbers. The thing that we will do in this class that's a little different from what other linear systems classes have done recently is we will use MATLAB quite a bit. And so if you've never worked with MATLAB before, you do need to download MATLAB because we will use it in the class, and you will be asked to do certain things in MATLAB on the projects and perhaps even on the quizzes. So MATLAB has certain commands that do some very useful things. This particular example that we're talking about, some useful commands are the absolute value command. So if you take a complex number and you type it into MATLAB command line with this syntax, then MATLAB will calculate the magnitude of the complex number. If you ask it for the angle, it'll calculate the angle. It will calculate the angle in radians. So in order to get to degrees, you multiply by 180 over pi, just right there in the MATLAB command line, and it'll give you the correct number in degrees. The other option is you do have the Cartesian to polar command that will convert Cartesian to polar coordinates. It is a really good idea to practice with MATLAB, and MATLAB can make your life a lot easier. It's also good because you don't have the ambiguity in MATLAB that you have associated with the calculator of the 180 degrees. So good idea to look into that. Okay, at this point I want to pause the presentation, and we will pick up with the next subject matter in the next video. In the last video, in sort of part 1 of this math review, we ended on converting complex numbers from Cartesian or rectangular form to polar, or what we'll refer to as phasor form. in this example, it's illustrated how to go the opposite direction. So this is just the application of Euler's formula, where you have some amplitude times e to the j phi. That's going to equal that amplitude times the cosine of phi plus j times sine of phi. So this is just an illustration of several examples where we have different complex numbers in polar form, and they're then represented in Cartesian form. So you can see how the cosine of theta plus j sine theta is plugged in with a specific angle. The sine and cosine are calculated. It's multiplied by the amplitude, and you end up getting a Cartesian form of a complex number. So this is 5 examples, actually 6 examples of how that's done. And furthermore, you can do this on MATLAB as well. The way to do it on MATLAB is to use the real and imaginary commands. So you can enter the polar form of the complex number just by using the appropriate syntax shown here. And so 2 times e to the j times pi over 3, and notice the exp command is for e, and then the multiplication is just for the magnitude, for the amplitude. So when you ask for real, it delivers the real part of the complex number. When you ask for imaginary, it delivers the imaginary part. So MATLAB will default to Cartesian form. So it's possible to just enter the complex number in polar form, and then MATLAB will do the calculation. There's also a command called polar to Cartesian, pol to cart, and that's a command that will also convert polar to Cartesian coordinates. So this is a very simple one-step process, shown a couple of different ways that you can do this conversion in MATLAB. So we can do a lot of just algebraic and mathematical operations on complex numbers. So here's an example of how to add to complex numbers. These complex numbers z1 and z2 are shown both in rectangular and polar form here. So I want to make the statement, and you probably know this, but if you are doing addition is much easier to do in rectangular form. You just add the real parts and add the imaginary parts to get the sum. So multiplication, it turns out, is quite a bit easier to do with complex numbers that are in polar form. So here we have z1 and z2, and these are just represented with symbolic representation r and theta. So we have z1, which is r1 e to the j theta 1, and z2 is r to the e j theta 2 times r2. If we multiply those two together, what you do is you multiply the amplitudes, and then when you multiply the two exponents together, that has the effect of adding whatever is in the exponent. So multiplication with complex numbers is very easy if you're in polar form. If you're in rectangular form, you can still do multiplication. The multiplication process becomes an algebraic multiplication of two binomial expressions, and that turns out to be pretty easy, but you do have to do, term-by-term multiplication. So always easier if you have things in polar form already and you need to do multiplication to just leave them in polar form. The same is true for division. If you have z1 divided by z2, then basically it's the magnitude of r1 divided by the magnitude of r2, and then the exponent will just be theta 1 minus theta 2 because theta 2 was here in the denominator. And then finally, if you have a complex number raised to a power, you can express that as r e to the j theta raised to the power, which is r to the power, and then the exponent has the effect of multiplying theta in the exponential, so it's e to the j n theta. Same is true if you're taking the nth root. You would take the nth root of the actual magnitude, but for the phase, for the e to the j theta, you would take j theta over n. So all of those are just generic illustrations of how multiplication, division, and raising to a power are accomplished with complex numbers in polar form. So here's an example of multiplication in Cartesian form. So we have z1 and z2 in this example. both shown in both rectangular and polar form. So in the Cartesian or rectangular form, you can see it is just the multiplication of these two numbers, and that's done term by term. So that's what's illustrated here in this line. Or as we previously illustrated, if you have them in polar form, you multiply the magnitudes and add the angle that's in the exponent. And likewise, division. So if we have division in rectangular form, notice we have rectangular form numerator and denominator. The way to do this is to multiply the numerator and denominator by the complex conjugate of the denominator. And what that does is that gets the imaginary part out of the denominator, giving you a rational fraction. And so you can accomplish that in rectangular form, although usually it's easier to convert first to polar form and do your division in polar form as is illustrated here. Likewise, MATLAB can really easily do multiplication. It can do it in either polar or rectangular form, and so that's illustrated here in this MATLAB script. The first part is just doing the rectangular form multiplication. The second part is doing that in exponential or polar form. And then finally, it's possible to do, just more complex operations. So this is just an illustration of just some mathematics associated with how we work with complex numbers. So we're given Z1 and Z2. They're both in polar form. So the first operation is subtraction. So much easier to do subtraction in rectangular form. So we first convert Z1 and Z2 to rectangular form, which is done here. Then, given the rectangular form, we can do the operation 2 times Z1 minus Z2. In the second part B, we're asked to find 1 over Z1, so we just invert that number, taking 1 and dividing it by the complex number, which ends up in this being this result here. Z1 over Z2 squared, the same thing, just a combination of operations that have already been illustrated. And then finally, looking at the cube root, when we have a cube root of something, we basically get 3 possible roots. So we can do that by assuming that we have some root k. When you have a root k, you can illustrate that in the following way. So here's the cube root of z2. So here's z2 to the 1/3. We plug in z2 in polar form, realizing that this pi over 3 can be expressed as pi over 3 plus 2 pi k, where k is any integer. So that's how we generate the repeated roots of a complex number. So if we were taking the 4th root, we'd have 4 possible values of k. Since we're taking the cube root, we have 3 possible values of k, realizing that this is an equivalent angle as long as k is an integer. So when we do that, we then take the cube root of the 8, and then we take the cube root of the exponential part. And of course, when you do that, 2 pi times k becomes 6 pi k, all to the 1/3. And then what you do is you let k take on different values, starting with 0. So the principal value is when you let k is equal to 0, and then you get this following result, 2e to the j pi over 9. When k is equal to 1, you get a different result. When k is equal to 2, you get a third result. And like I said, if we were looking for the 4th root, we would let k take on 4 different values. So that's how you take a root of a complex number. You always want to do that from polar form. Almost impossible to do that in rectangular form. And then finally, it is possible if we have unknowns in our expression for the complex number. So in this particular case, we've got some real variable omega, and we're given a complex number that is a function of omega called x of omega, and we want to express that in Cartesian form. We want to find its real and imaginary parts. So the first thing that we do, obviously this gets almost impossible to do in MATLAB because omega is a variable. So the first thing we do is we make this a rational number or a rational fraction by getting the imaginary part out of the denominator. So we multiply numerator and denominator by the complex conjugate, which is done right here. Let me get a pencil. So that's done right here, multiplication by the complex conjugate. You notice that then gives you a real only denominator. And then in the numerator, you want to group such that you have a real part and an imaginary part. And then once you have that, you separate it into its two components, the real component and the imaginary component. So this is in Cartesian form, and the real and imaginary parts are each functions of omega. Now, if we want to do that in polar form, we convert both the numerator and the denominator to polar form. So remember, the conversion goes that the magnitude is the square root of the real part squared plus the imaginary part squared, shown here and here for the numerator. And then it's e to the j, and the phase angle is the inverse tangent of, if you recall, it is going to be the imaginary part over the real part. And obviously j is not included when we say quote-unquote imaginary part. So that becomes this expression. We can then combine that into a magnitude, which involves the two magnitude terms, and then a phase part, which involves the difference in the phase angle in the exponent. So that's a polar representation. So the magnitude of x is shown here, and the phase is shown here. This is a fairly common thing that you'll have to do when finding magnitude and phase of different, especially in like filtering applications, of different frequencies. So I want to conclude the lecture on complex numbers here, and we will start with the next video on sinusoids.